But case histories are always pretty fun. It's always good to learn from mistakes. And case history is nobody in this room, so nobody has anything to worry about. But they're always interesting, always good to learn from. Particularly with large diameter tanks, there's unique situations presented with just a larger geometry. Things kind of scale up and expand a little bit. So we'll talk about a recent case history that we dealt with a couple, 2 or 3 large diameter tanks. Talk about observations, challenges, and ultimately lessons learned, so you guys can learn from others' mistakes. But before we get into the actual case history, if you've noticed somewhat of a theme so far today, and it'll go into tomorrow a little bit also, is reliability. Reliability is paramount today. Safety is always a critical concern, we understand that, but your plants are making a lot of money. You want to keep them up. You don't want unplanned outages. You want to keep your equipment lasting years and years and years and years. And I don't know how long or how many times we're asked, can we just get a couple more years or another cycle out of this tank? So you guys are making a lot of money. Even coming down for a normal outage is not as desirable, let alone unplanned outages. So again, just reliability. We keep coming back to this theme, so we're going to be talking about that again today, and how, if you know this step to ensure reliability, how can you prevent these types of things that we witnessed in the case history from happening? If you don't know the right steps, then you can't identify them before you actually get to them. So that's sort of the purpose of this. So when we start projects, when we're going, soup to nuts on a project, how do we make sure you start out on the right page here, on the right path? And that's really starting with specifications. If you don't know the right steps to make sure the project starts out on the right path, you don't know what's preventable. If you do know the steps, you can get out ahead of issues before they actually happen. So that goes with specifications. I'm going to talk a little bit more in depth about these: vendor selection, project planning, going through the bid process, which is a lot more important than you might think, especially if you don't really know if you don't know FRP very well. The bid process could be one of the more important parts of your project, through startup, fabrication and testing, and then finally through assembly. So what makes a quality specification? Okay, you have your fluid contents, you have your service conditions. We've talked about this a little bit, but they need to be clearly stated: specific gravities, chemical concentrations, pHs, temperatures, all that stuff. What design standard are you going to invoke? Is it going to be a stamped tank? Is it going to be $32.99 for a film and wound storage tank, $40.97? Tom had a good presentation earlier explaining the differences. Personally, we'd like to default to RTP1. We understand it's not always realistic, but we would like to default to that because it gives a lot more guidance, it gives you a lot more teeth. But just know you can't just define RTP1 unstamped and expect everything to work out well. So there's more that goes into that. So in terms of this specification, we have an example of a data sheet we give. So it's not just a performance specification. We need detailed, we need prescriptive specifications. You want to get down to the nitty gritty of what's acceptable, what kind of materials of construction, what are your corrosion barrier composition, what resin do you want? I prefer not even to say or equal. The manufacturer may ask that, and you may consider it, but just tell them what you want. You don't have to acquiesce to their standard product, but if it does make sense, I don't have a problem accepting it. But I would rather start with what you want and only give in if there's a certain delay in delivery and everything is a functionally equivalent substitution. What fabrication methods do you want? There are owners out there, believe it or not, that still maintain that a hand layup, remember our terminology from earlier, shell is the best. It's the most corrosion resistant. So they'll make the entire shell out of alternating Madden woven roving, even if it's 10-foot diameter, 12-foot diameter, because they maintain it more corrosion resistant because it's got the highest resin content. I personally don't ascribe to that because the structural wall should not be seeing that surface at all. So just make the corrosion barrier really, really well. If you need to make it a little thicker, that's fine. But you can have a film and wound structural wall, but that's up to the manufacturer. But you have to clearly define what you want. Visual inspection level. Tom mentioned a little bit. You have level 1, which is near perfect, level 2, which is a little bit worse, but it's, well, a little bit worse than perfect, but still acceptable for a lot of cases. There are certain elements, and this is where you need a good consultant or somebody you rely on. There are certain elements of a visual inspection criteria that you still have to define. You can't, beyond just saying level 2, like the number of gaseous bubbles and blisters, that's a constant, I would say sticking point, but more fighting point between us and a manufacturer, because we're kind of on opposite ends, where a fabricator wants a little bit more leeway, we want it to be a little more strict. But those are not defined in R2-1, so if you don't define it, they're going to decide it for you, and it's usually to their advantage, not necessarily to your advantage. And finally, what are the testing requirements? Are you going to require a post-cure? Do you require a hydrostatic test? Is there a vacuum condition that you want tested on that? You can go so far as to require acoustic emission testing. If you don't know what that is, we can talk about that offline. But some owners acoustic emission test every single vessel that comes into their plant. They see that much value in it, but you would have to define that. So all of these things go into a quality specification. If you're missing those are gaps, and there's going to be gray areas. When you go out to bid, they're going to fill in the blanks for you. And that's how you start getting apples and oranges comparisons, not apples to apples comparisons. So that's how you get the one that's 30% lower cost than the other 3. Because the other 3 might be maybe a little bit more reputable. And we talked about even stamp holders if it's an unstamped tank, you have certain stamp holders that will still quote you a really, really decent tank. There are other manufacturers that have 2 different quality programs depending on how much they think they can get away with. And those are the ones that you need to hold their feet to the fire, but you can't do that without a quality specification. So you want to pre-qualify your bidders. Tom had this in his presentation. He likes to say fabricators are living, breathing organisms. Who you thought was really good 5 years ago, maybe they're not so good anymore. There's been a lot of turnover in everybody's industries lately. So who was good 5 years ago may not be so good right now. Who did a bad job for you 8 years ago, maybe they've improved. Maybe they've turned things around, implemented different procedures in-house. So maybe now they're worth a visit to your bid list. As we've been talking, the available manufacturers list has been dwindling down a little bit. So we get asked constantly, hey, who else is out there? So there are people out there, you might not know them, you might have had a bad experience with them in the past, so just go to their shop and conduct a shop audit. Review their QC program. Hopefully they have a decent one. Evaluate what they're doing for best practices. Are they doing things in accordance with what you know to be best industry standards? Maybe you don't know what best industry standards are. So we do shop audits for you. We have a checklist that we're going through. We're talking to them. We're understanding what they're doing. We know where they're maybe cutting corners a little bit, and we provide that feedback to you. It helps you make your decisions. What's their capacity? Do they even have capacity? If they have capacity right now, I'd be very, very shocked, which is why we've been talking about planning ahead of time nowadays. What are their capabilities? They should be able to adapt to your needs. You shouldn't be agreeable to everything they want to do. That manufacturers have their way of doing things, and sometimes it's all well and good. I'd rather them do something they're comfortable with, as opposed to me forcing them to do something that they don't do as well. You're probably going to get a better product, as long as you're okay with it, as long as you fully vetted it out and you're okay with it. But it's your project, it's not their project. They don't get to decide, you do. Look at their process and cleanliness. If you've learned one thing about Tom so far today, he's got many pet peeves, and cleanliness is one of them. He's a firstborn. He likes things very, very ordered. If you saw his office versus my office, his is very, very well kept up. Mine's a little bit messier, but not quite like a dirty fab shop. Yeah. So that matters. A dirty shop, yes, it's going to be a little bit dirty, but are things just all over the place, not easily identified? All of that matters. All of that goes back to more or less their priorities. We've talked a little bit about certified bonders, laminators, welders. To us, certification should be mandatory. If you were having any kind of steel pipe, any steel tank welds being done, you would ask for their certifications. You wouldn't let a welder on site if they didn't have their certifications. It should be no different for FRP. You should be making sure that they have their certifications. All of their laminators, bonders are certified. There's in RTP 1, one of the mandatory appendices clearly defines these standards to get them certified. Just ask for this. Do you even know that was a thing? Have you asked them these questions? You may not know, so that's where you get maybe these A teams, these B teams, C teams, and where you're getting these bidders that are a little bit lower cost than the others because they don't see in the specs that you are making them use their certified bonders and laminators. So they're going to try to cut corners where they can because they're out to make money just like all the rest of us. So we recommend RTP certified manufacturers. There's no way around that. I mean, we do recommend it. They deserve to be considered. They've gone through a rigorous process. Not every tank needs to be stamped realistically. We've talked about water tanks or just holding salt water or just very, very simple tanks or emergency tanks that hold fire water. Not every tank needs a stamp. Sometimes, unfortunately, schedule precludes a stamp because you need it quicker than can reasonably be done because the UBRS is a little bit of a sticking point. When you do a stamped tank, it tends to delay the project a little bit. So sometimes you just need a tank really, really quick, and we can't recommend a stamp in that case. But if the vendors, we would still recommend having the stamp holders on the bid list. We feel that they've done their due diligence. They deserve to be considered for on your bids. But if vendors aren't certified, that just means it's even more critical to audit the shops, to review their calculations and drawings. Jeff was saying they may have one engineer in-house that does storage tanks really, really, really well. Nobody's ever reviewed his work. He's using a save as template from the previous guy that retired. And you give him a little bit of a unique project, he can't think outside of the box. There are design rules in RTP, but not for internal structures or tall tanks for the bottom knuckle to do the detailed FEA, and they might not have anybody reviewing their calcs. So if you're not comfortable, have somebody review the calcs and drawings, have the prefab meeting. We're big on this. Go through the spec line by line, talk with their shop manager, talk with their QC guy, make sure you got the ITP in place, make sure you know what the hold points are, what are the appropriate materials of construction, are you okay with this? Read this line, do you agree with this, do you not agree with this? Just have that meeting, lays all the cards out on the table. Then finally, especially if they're not certified, you want an inspecting process, you want to witness a test. So if you have a stamped tank, theoretically, you don't need Maverick to do your inspections because that is ASME is the ones that will be auditing their process. So we would make less inspection visits for stamped tanks, but I think we serve a good enough as a liaison for a fabricator that they still use us. But when you don't have a stamped tank, then it's kind of like the old Wild West, especially if you don't have a good spec and you don't have somebody of your own subject matter expert that knows what to do when they go into their shop. I'm not sure how well you can see it, but it's in your slides. Somebody did talk about the list. I think Steven mentioned that there's a resource out there to research the ASME stamp holders. So I feel they should get some recognition, so you're welcome for putting you guys on here. We are down a few. It's been, in the past few years, 12 or 13, and I think you can count on there 10, maybe? 9 in US, 1 in Canada. So we're down a few. Some of the shops have consolidated, some have closed, some have not renewed their stamp, so that means fewer options. And that's even before all the issues now with resin shortages and other things like that. So it means more manufacturers are being entertained as possibilities for your projects, which means you need to do your due diligence in making sure that they're qualified to be building for your project. Shipping and handling, Tom did cover this. How do you want your tank to arrive? Are you specifying, are you okay with, your high, your critical asset coming in on carpet rolls or or a stack of tires. Will it come with cradles? You know, some of the tanks do come with cradles, some don't. Are you planning on installing it right away? Is it going to sit in your yard for a while? Is it going to sit in your yard for a while? It can embrittle a little bit, sort of like dry rot, so you may want to protect it a little bit. Or on the other hand, if you're repurposing a vessel and some of those haven't been in service for a little while, you got to be careful of these vessels just sitting out in the sun for a while. So if they are just sitting around, try to cover them so they're not exposed to the elements. So make sure you set your expectations. Don't assume, obviously be clear, thorough documentation. Just like a steel vessel, the same process works for FRP. Communication is key, those prefab meetings, routine meetings, you know, every week during the project. It helps to make sure that they're providing good care and good diligence for your project, make sure that it's getting good attention, demand the best practices, know that there are standards that have good best practices out there, so you're not just relying on them. But make them prove it to you. Make them prove it to you, make them prove it to us, to ASME in the case of a stamp tank. You know, you want to get what you want, not what the manufacturers necessarily want to give you. So, again, these keys, and then we'll get into the case history here. Detailed specification, good vendors, setting expectations from beginning to end, and then QA, QC throughout the process. Standards change. We're constantly updating them. If you have internal company specs that are 5 years old, they're probably out of date, so you may want to consider revising your specs. That especially goes for piping. B31 1 and 3 are probably throughout your piping specs, whereas now ASME M2 was first issued in 2018-19 and is now the preeminent pressure piping standard for FRP. So if you follow this recipe, I mean, the chance for success is extremely high. There's black eyes in the non-metallic industry, there's black eyes in every industry, but there are some owners who swear off FRP because they've gotten burned, they're tired of unplanned outages, so they just say, you know, forget it, I'll just replace it all with titanium. There's manufacturers out there. It doesn't have to be this way. If you follow these steps, the chance for success is extremely, extremely high. Large diameter tanks, I'm jumping off of what Mike presented earlier with the ovation and the field fabricated. So just to reiterate, and by the way, I'm okay, you're hearing some of the same message a few times today. I'm completely okay with that. I think it's actually good, especially if you're not as familiar with the process. I think repeatability helps to commit to memory. You know, what do they say? Like it takes 21 days to make a new habit, and it only takes like 1 or 2 days to make a bad habit. I'll say this 21 times if I have to help commit some of these things to memory. So revisiting things, it's, you know, obviously we're all doing our own presentations and there is overlap and we'll talk about different things, but I think that's good. I think it helps to reinforce the things that are pretty important to us. And I mean, we're the experts, we're in this every day, we're seeing this stuff, so if we're repeating it, we really, really want you guys to pay attention to it. So with the large diameter tanks, typically ranging from 15 up to 120 foot, like Mike said, that's I think 119 maybe with the OD it got to 120. Yeah, so they can be shop fabricated and bladed, they can be totally field wound and constructed, which brings its own challenges because essentially you're bringing the shop to the field. It takes a couple months to set up. You need a temporary shelter because now you need your shop environment with your ambient conditions, everything controlled, humidity controlled. You need to bring that to the field, which is very, very challenging. So for our case history, they had an early decision to make. And by the way, we weren't involved at this point, which is why it made a case history, because we got brought in later to help them diagnose and get some lessons learned on it. And by the way, I'll say this now, it may not be good to say, but I've cost my customers a fair amount of money over the years because we're not involved early enough, and they end up having to pay for it eventually, but they've gone through the bid process and awarded a low bidder, and they get change ordered to death. But it's like, when you bring us in after the fact, you're gonna end up paying that money. You're gonna pay the same amount of money, maybe even more, in delays or change orders, then you would have paid the other vendor, or the other bidder that was a little bit more expensive during the original bid phase. So yeah, it's maybe not great to admit, but yeah, I think I've cost my customers a fair amount of money just to get what they should have gotten if we were involved early on, or if they had their own SME in place. So ablation's been done for decades. It's innovative, it's unique. There is a demanding design aspect of it. There's some drawbacks. We talked about safety issues. We talked about brittle resins not being able to be ablated quite well. There is more of a maximum size in what you can ablate because you still got to ship it. That's the point of squeezing it down. Well, when you squeeze it down, now it becomes a really big oval, and now you can't fit it on a truck. So there's just logistical issues with ablation. So in that case, you might want to go to field winding on the plant site. So there are plenty of additional concerns with that. The growth of the floor, the larger diameter means the walls have to get thicker. Your head is probably made in segments, so now you're doing more of a pie-shaped design or a scallop design. Maybe you need a shallow head because you have a platform going overhead, so it takes quite a bit of pencil sharpening to design a large diameter tank. Everything scales up. A lot of the mechanics equations scale up, but there are certain aspects that aren't quite captured in just engineering calculations. But I mean, you got quality concerns. You have to build that temporary enclosure, emissions permitting. You have to decide, who's giving me the electrical power and different safety implications there. Okay, how about door number 3 then? So this manufacturer tried just the old tried and true method of saying, okay, well we'll just shop wind and we'll just ship a large shell. We'll just take out 2 lanes of the road instead of trying to ablate it down to 1. So this does create logistical issues, as you'll see, but if it's okay for over the road, I guess if you can get those permits and get the DOT to sign off on it, we've seen 18-foot, 19-foot diameter shipped over the road unablated, not a problem. So maybe 28-foot diameter could do that. That seems, it seems like asking a lot, but the manufacturer convinced them that they could ship a 28-foot diameter by 25-foot high over the road. So they built it in 2 segments where the bottom half is made in the shop, top half is made. They could join the top head to the top shell, flat bottom to the bottom shell, ship those 2, and now they just have 1 field joint. So you can imagine how they're becoming a lot more cost competitive now because they convinced the owner that they could ship this over the road. They don't have to go through the ablation process. They don't have to ship the heads disassembled and have 2 extra joints in the field. So they did a good job of convincing the owner. We started to get involved because we're on that plant site for other things, and we started catching wind of what they're doing, and we're like, So we had a decent relationship with the customer at that point to where they finally believed us, so we started to get involved. But the bid was already awarded. Now they got the low bidder in there, so now they're about to get change ordered to death. So what's that recipe again? Project specification, project planning, vendor audit, bid review, design review, ITP, inspection test plan, making sure they got good hold points. What QC points, what QC values, what testing are they doing in process to be able to prove their manufacturing, and then QA, QC throughout the process. So that's the recipe of a successful project. So you can read it. The solid red was not done. The dotted red was eventually done by us. But again, after the fact, now I'm going to cost you a lot of money. If you're going to make me do the design review after they've already done their preliminary sizing, now I got to review the calcs, and I'm going to find a lot of issues with it. I'm really good at that. So it ends up costing them money. But there's no project specification. I think they said D3299. They gave them specific gravity, and hey, you run with this, I'll trust you. No bid review that I'm aware of, and if there was, they were bidding against people that knew it probably should have been ablated. So yes, the ablation cost was going to be higher than shop building and shipping. All right, we're not reviewing calcs here, but granted, I had a little bit more time to review this, and you could probably read it pretty well. But there's a few things that jump out at me that might not jump out at you, and might show you that I shouldn't be trusting the manufacturers then. So Tom talks about pet peeves. This is pet peeves of mine. This is not 1995 with old, I don't even know if I didn't do calcs back then. I was still in elementary school. But they have the units here, which was done back in the day. They didn't have units in their programs, but there's no units over there. So they're already working on an old method where you're trusting just that their values are matching up. Whereas if you have units in the inputs, that's going to tell you if you have an issue. So that's red flag number one when I see that. So just so you know, this type of equal sign means they're defining a value. They're defining a quantity. So okay, they're defining a design factor 10. Good. Liquid height. Good. Why is that spacing off? It's jumping out at me that they're just manually typing this in. That's not from an actual program. So all these red flags are going off. You have this equal sign means it's a calculated value. These aren't defined anywhere. So they're hidden somewhere. They could be off to the side. You don't know what math is being done to get to some of these values. So all of these things are kind of going together where I don't have a lot of faith when I'm looking at this calc. You might look at it and be like, well, it looks pretty good. They're doing their wall thickness for hoop stress and axial stress. They don't give me what the value equals. It was nowhere in the calcs. Select the thickness of the two values. Okay, what is it? We don't have it. Then all of a sudden, they just give us a minimum wall thickness. It's not the same variable. So where are these numbers coming from? And then they finally just chose a number. But all this might just go over your head if you're like, oh, well, they're engineers. Surely I can trust them. Maybe not so much. Back to the units. So just an example, and this is straight from their calc. I just took a screenshot. So units for this pound over inch plus inch. That equals pound per inch, and they have units of PSI, pounds per square inch. If they had units in their equations, in their values that they input, that would not have checked out. They'd have gotten a weird number and they'd have realized that something was not quite right, but hey, it's okay. I don't know how it's okay, but somehow it's okay. This is my last this is my pet peeve where I get a little worked up. Tom in the back, and probably. Yeah, okay, so I feel a little bit, I'm sure you've all have seen the matrix. I'm like the operator in the matrix that can read all those values going down, and they know exactly what's going on inside the matrix, and you look at it from the outside, you're like, it's a foreign language, I don't know what's going on. So this is an example of a laminate sequence. So we have laminate analysis programs. You can input each layer by layer. Here's our veil, mat, uni, winding, everything I talked about in the 101 earlier today. So you basically build your laminate and you're supposed to get results. Sidebar, they didn't give us any results, they just gave us the laminate sequence. But there are at least 5 things just in this little snippet here that caused me to question. Just same thing like with the calculations. So this, on layer 3 here with the mat, standard 43 mils, you're gonna see that pretty commonly. It's a standard mat thickness, ounce and a half per square foot weight, which gives you about 30% weight percentage. Okay, the next layer here, they say it's a chop. Okay, it's half of that thickness, which means I would think it's about 0.75, so they have a little bit higher glass content, giving a little higher property. Maybe it's right, maybe they calibrate their chop a little different, but again, it's just a question that I'm bringing up. But then you look down here, okay, we have our same 22 mil chop cycle, the next layer is 11 mil, so shouldn't that number be half of that? Well, no, the glass content's higher. Their properties are creeping up by doing this. Down here is just completely impractical. They finally have a hoop winding, and their glass content's 90%. They don't intend that. It's just an error, but they don't know what they're doing. You might look at that and be like, well, that's pretty good. I'm gonna get a good elastic modulus with that. I think rule of thumb is anything over maybe 76% glass is not, it doesn't act as a laminate in that sense. It's too dry. You don't bind the glass windings together. So right there, that's a pretty big red flag. This is more, that was that 201, 301 class where I said we're not going to get into, but there are certain ways you want to lay up a sequence to get good balance and symmetry. They didn't do that, so we had to go back to the drawing board on that one. And then finally, more pet peeves. They got weird indentations, so I still think that they're manually typing in certain things. So just in 15 layers here, I found 5 things that made me question, coupled with the calculation. So yeah, I'm about to cost somebody some money. In delays too, because to get from Rev 0 to Rev 15 takes a long time. So, just some of the things that changed from Rev 0 to Rev 15. The top shell, 652 to 743. Not that big a deal. I don't remember the exact details. I'm pretty sure the top was designed for vacuum, so maybe it was governing, so it didn't increase too much. Bottom shell was 0.765. Remember, this is a 28-foot tank. Now all of a sudden it's 1.371 when they did the right sequence. So remember that 90% glass that they had in that winding, that gave them properties that were completely unrealistic, which is where they calculated that number. So now all of a sudden somebody's got to pay for an extra, 0.8 inches of laminate on that bottom shell. Maybe it was absorbed by the manufacturer, I don't know, but somebody's got to pay for that. They changed the sequences, what I was saying, where they didn't balance it quite well. Top head, it was a flat top head. If you know anything about a 28-foot diameter tank with a flat top head, that's like a trampoline when you're walking across it. So it needs to be pretty thick, pretty stiff. Their first attempt had 1/2-inch balsa core, and eventually they had 2-inch balsa core, and their plies, their skins, inner and outer skins, also about doubled in thickness. All of that from a calculation review. All of that could have been avoided if they did a little more due diligence up front. Okay, finally, design's approved. We got Rev 15. They probably started building around Rev 10, let's be honest, but things happened and they kept going. So, do you have an ITP? Who is actually doing the QA, QC? Have the whole points been communicated? We came in after the first shell was already done. At that point, if something's really wrong, then you're forced to reject it. So the owner would need to make the decision, do we need to do constant surveillance? Usually we like to go in intermittently, so we're not just running up cost, and we try to go in at the important points of fabrication. But you can decide to have it the whole time as well, especially if you're not fully trusting the manufacturer. These prefab meetings are important because you communicate your expectations to them. And then they are forced to communicate their expectations with the laborers in the shop. The laborers don't always know what's important. In this case, maybe a little bit dark, there's a big gap here. So this is a uni-layer. Remember that's providing axial strength. So you have hoop winds, and then you're providing uni-layers to provide axial strength. The overlaps, just like they are in the corrosion barrier to make sure you're getting full thickness. If you don't overlap those unis aren't doing anything. You're not transferring load from this layer to this layer, so that would have to be either rejected and rebuilt, or they would have to add thickness, more layers to that, and just basically say that's sacrificial layer. But that's the risk of building things before we get there, or building things without a good prefab meeting, without making sure the shop has good internal QA, QC. This was a learning experience for me. So this is a mold for a head where they use something called peel ply. I didn't know what peel ply was until our inspector found it, because our inspector is really, really good. And it wasn't even Tom, as a matter of fact. Peel ply is used in certain cases, I guess, to minimize grinding dust. Very rarely used in the corrosion industry. Our inspector theorized that they just thought that was veil. So if we're not there, if that guy's not there while they're building that, well, they put the structural laminate over that. That's going to go to the site, go on a harsh service, and that layer is probably going to need a reline really, really quick. Relines are never as good as the original part, so we caught this in time. We're able to get the right materials added to the part. Now, who decides what's acceptable? If you don't have good specs, if you're not specifying certain standards, defining the tolerances. 28-foot diameter head, it's going to sag a little bit. You're going to have a natural sag. Usually it's 1/2 inch deflection or 0.5% of the diameter, which 1/2 inch would be governed on something like this. But if you don't have spec in place, what's stopping them from using 1 inch? Are you comfortable with walking over, say, an HCl tank? Something holding HCl that is, flexing underneath you, flexing 1 inch or 2. It may not be overstressed, but I wouldn't be comfortable doing this. Well, what if this was the bottom head? What if this was a flat bottom? Is that going to come back into place, or are you going to now have point loads wherever it is resting? Sometimes you have oil canning. You might have heard that terminology for a more flexible tank. Sometimes that flat bottom comes back in, sometimes it doesn't. If you don't have a spec to define that, you don't have anything to hold them to. Shells are flexible. We talked about ablation. They have to be flexible if you're going to ablate them, but sometimes they come out of round. Those are shipped to site. Now you might have a gap of 3 or 4 inches. Is that acceptable? Will that come back? Will you have cracking, depending on what resin was used there? Jeff mentioned the nozzles. If you don't have, so RTP1 fortunately does define the permissible gap around nozzles. Overcutting is never a good idea. We've been called in on probably $50 million failures because of simple overcutting like that, where it's causing somebody lost their job on that one. But the standard on this one was ASTM D3299. They don't have tolerances on openings. So they might fill that with putty. If you're lucky, they'll fill it with what we would call maybe a resin grout or something like that, where it's milled fibers mixed in putty, and they'll stick it in there and try to fill it in as best as possible. Most likely, if you're not there, they're just going to fill it with putty, and now you're going to have delaminations. Your nozzle loads are going to go way down, and it could be a potential leak point. If you don't have specs in place, you can't do anything. Well, you can make sure you pay for it. Remember, it costs them money because it's like, well, you shouldn't allow that. So proper oversight, dimensional confirmation is key. Watching them do this in process is best. Most of these guys want to do good work. Some of them just don't know how. They haven't been properly trained, properly communicated. So trust, but verify. The handling on these larger parts go up. That's a heck of a nickel or a quarter if that were to kind of let go and spin around. That's a safety hazard. You got to make sure the shops are set up to handle this. Where do you lift on things like that? We know it's pretty flexible, so you have to actually pay attention to the lifting when you have large parts like that. I believe Jeff mentioned earlier, anything secondary, anything where somebody's hand is applying it, anything hand lab, contacted, molded, could potentially be a leak point. We got thick shells, we got a lot of nozzles, a lot of reinforcements, internal flanges, a couple elbows. There's a lot going on these vessels that you want to make sure, because all of these are going to be in the liquid level, so every single one of these is a potential leak point. So proper surface preparation, cleanliness of the shop, making sure you're getting all the grinding dust off, and again, using certified bonders and laminators for this QA throughout the entire process. Sometimes you have unexpected complications. It can be difficult to make a hole when the bottom is 6 1/4 inches thick when all was said and done. Would any design decisions have been changed if they knew when they bid the project that their bottom knuckle was going to be 6 1/2 inches thick? They might have tried a different shell construction. They might have tried a different knuckle arrangement. There are more efficient knuckle arrangements than something like this. But all these kind of problems compounded because they didn't know what they're getting into. They wanted to win a job. They thought it was a good job to win. Well, what about nozzle projections? Sometimes you say 6 inches from the ID. Well, that's not going to work with a 6 1/4 inch thick shell. Technically, RTP says from the OD, so it's kind of tough on the owners because the OD changes. It means you have to change your projections. But were any of these considered? Are the piping connections now going to have to change? Likely they will in the bottom if everything's a little bit thicker. And finally, that OD, now instead of a 28-foot, 4-inch OD is now 29-foot. 28-foot was already too much for us. But they did it. They had to cut off many nozzles because it wouldn't fit. So they had to cut off the nozzles and now reinstall them in the field. So now we have secondary laminates done in the field in a non-shop environment. So these issues keep compounding because of poor planning, poor decision making, poor specs. All right, getting close to the end here. That issue with kind of the flattening that is not completely unusual. I mean, this can be brought in as long as you're watching. If you're not watching, they might just fill that in. Jeff said maybe throw a 1/2 inch thick laminate on the top of that. They'll never know. Tomorrow we got a case history that'll expose this a little bit more. If that doesn't come in, you can build what we call more like a shear ledge, where we just come up straight up and make the shell a little bit thicker to match that up. But usually on larger diameter shells, that'll come in as long as you pay attention to it. Everything scales up. So these repads got really thick. Is a big problem. Tapers in FRP should be about 6:1, so that means for every inch of thickness, this should be tapered down 6 inches at a time. So 6 inches per inch of tapering down. That is maybe 45 degrees, whereas 6:1 is about 10 degrees. This would be a problem if we let that go. You got this huge block of laminate on there, inches thick, on a shell which is still thick, but it's still 28-foot diameter, so you still have flexibility in that shell. So when you load that up, this block is not letting this flex. So there's been major failures from poor repad installation, poor bonds, poor taper, where the man weight completely popped off on large diameter tanks. And further, you probably can't get the bolts in that repad anyway, so you'd have wanted to make that projection a little bit longer. Field environment is not the same. Expect delays when you can't control the environment unless you build a temporary enclosure, but it's still gonna be challenging. The guys are not working in their normal environments. They like sleeping in their own beds. When you send them to the field for months at a time, quality goes down. It's gonna be delays. So you got union workers, maybe a little bit more challenging to get things done. If you need post-curing, other kinds of testing, everything just gets more complicated in the field. So I get why they wanted to do as much as possible in the shop, but they still needed to do stuff in the field anyways. And then finally, if you can't see it, their foundation, it didn't fit on the foundation. So it goes back into planning. They didn't expect to have a 6 1/4 inch thick knuckle at the bottom. They expected a few inches less. You can't get the whole downloads on there, they're over here. So they needed to build out the foundation just to get this tank to fit because of all the issues that they didn't correctly address at the beginning of the project. One last time, specifications, vendor selection, good planning, not just some planning, but good planning. That bid review process, very, very important. Make sure you're eating apples to apples. Review those exceptions that they're putting in the fine print at the end. Review those. Make sure what they're trying to get away with. Sometimes you can accept the exceptions. Sometimes you want to maintain it. But if they're taking a bunch of exceptions, that means their cost just got a lot lower. If you're saying, okay, well, I don't accept that exception, now their price is going to go up. Now you're getting more in line with your different manufacturers. So yeah, to beat a dead horse, other manufacturers would have been considered. I really doubt this vessel would have been built like it was. I think it would have been ablated. I think it would have been more expensive. I believe they spent more for these tanks than they would have if they would have just went to the manufacturers that ablated them. But it all started by not following the recipe, not following the process of having good specs and planning early on. So with that, any questions? Yes?
The tank wall was, or is it just a knuckle that's 6 inches thick?
It was a knuckle, yeah. So one of those slides, I think it came out to about 1 3/8 maybe for the structural wall of the bottom shell. And then because the bottom knuckle is made of type 2, so the type 2 laminates, and depending on how, if they made their shell very, very efficient, very, very stiff, it's gonna have high properties. So now you have the knuckle that's type 2, which is probably 40% of the properties. So now you're talking about the math to make up the extra thickness, and they might have had welds over there too, nozzle insulation or repad.
Still, like a 3-inch thick shell to avoid that seems almost unreasonable, right?
I agree. Same question earlier about oblating pipe. There's a certain size that's pretty unreasonable if it's too stiff. But you can do FEA to do that tech. Like their RTP has requirements for measuring strain to make sure you're not cracking the liner. It's a little bit higher than I would recommend, honestly. But yeah, it doesn't let you use 470 for that, which would be a stiffer resin. If the numbers prove it, I'm okay with it. But yeah, 3 inches probably I've heard people ablate thick shells. I don't know the exact number, but I just had this conversation a few months ago where he was like, yeah, we've ablated thick shells. That's a lot of stored energy when you compress it though.
Yeah. So in truth, I mean, you've seen like a couple mentions of like the 120-foot diameter. Those were field fabricated. Those shells were only 3.5 inches. We got pieces of laminate on those shells. So you saw here, some of them were the bottom was as thick as 6 inches. That was because of manufacturing oversights or their process. That wasn't because the design said it had to be that thick. That tank there did not have to be, it had a 3-inch shell. Probably could have been in 1 3/4, something like that, probably, maybe 2 inches.
Sure. It was high specific gravity, but yeah, it could have been optimized.
I mean, there could have been other optimizations.
And so that was the extreme thickness of that was, some of that was driven by the fact that they started fab
The
correctly.
way they manufacture.
Right, okay.
So we haven't talked about it yet today, but on larger diameter tanks, they usually are made with flex knuckles. So the shell is just built straight to the ground, which is good because it bears right on concrete. And then you have individual panels of floor that are fit in a manway or something like that, and you weld those all together, and then you just do a secondary joint from the floor up the shell. But that's just to allow for a little bit of movement, a little bit of flex. When you fill it up, it's going to expand a little bit out. So it's very flexible. It's not thick at all, but all that load is taken by the shell. If you have a curved knuckle, you can imagine. I mean, you're an engineer. You know it's got to get a lot thicker because you need a big radius, and you have a lot of stresses in that knuckle because of the diameter of the tank and specific gravity and the weight on it. So yeah, they wouldn't have done a hard knuckle like that. They probably would have done a flex knuckle. Yes.
So in this example, when did you guys exactly get called in to help, or what was the breaking point, or what went wrong? That they're like, all right.
I was talking about that with Jeff. He had more conversations, but tomorrow we have another case study. Tom and I are presenting. It's the same facility, different project, but that's helped to illuminate them to their need for a fiberglass expert. So then once we were doing work in and around that area, oh, what's going there? Oh, 28-foot tanks. Are those ablated? No? Huh. Okay, and then you just have those conversations. But it was after the bid process.